Hello students. The purpose of this video is to look at some of the processes that would occur in this sort of room. This is a metal room in a fairly modern trade training centre. But to look at the processes that would happen in here, but then also to look at how they would operate in an industrial context. So recently I visited a company in Reed called Curtin Engineering, and they are currently in the process of building a drying unit for ore production for a major mining client. And so I had a look at some of the processes that they were using there to manufacture that. The processes that I'll be looking at specifically are how metal is cut, how it is shaped, how it is bent, how it is joined, and how it is finished. And we'll have a look around here as well and look at some of the different machinery that is used in a space like this, and we'll be able to compare it with that out there in the real world in an industrial context. So firstly, let's have a look at how we would cut metal. Now in a situation like this, cutting metal may range from using a pair of aviation snicks, to using a guillotine. This is a fairly good sized guillotine and it's fairly modern, but we'll see by our look at industry that guillotines used there can be much bigger than something like this. There's a couple of other machines here which we're going to have a look at as well. Two other pieces of equipment that are used in schools for cutting metal is the oxyacetylene, and more recently schools are getting these plasma sets as well. Now these plasma sets are fairly inexpensive, they only cost about $800 each, but there are much larger versions of this that can cut much more significant amounts of metal. The oxyacetylene is quite useful as well because not only can it be used for cutting, but it can also be used for brazing processes, heating processes as well, which is what it's being used for right now.
Here we can see an example of oxyacetylene cutting. Because this is a straight cut, a guide is being used along with a plate mate, which is a mechanical feed unit produced by Sigwell. In this case, he is cutting a curved section of 50mm plate steel. It is curved to the outside dimensions of a drum roller being constructed. The cut sections are to be the teeth for a drive unit on the drum roller. You may be able to see the completed sections here attached to the outside of the drum. This 5-metre diameter drum is part of an ore drying mill being constructed for the mining industry. Curtin used a number of other cutting processes. This is a large CNC cutting bed that can use either oxyacetylene or plasma as the cutting process. Their plasma cutter has the capacity to cut up to 32mm thick plate. This guillotine is hydraulically operated and can cut steel up to 6mm thick. This cutting process is known as air carbon arc gouging. An electric arc is generated between the tip of a hollow carbon electrode and the workpiece. The metal becomes molten and a high velocity air jet streams down the electrode to blow it away. The process uses the same equipment as gas metal arc welding, with some modifications, has a high metal removal rate, and the gouge profile can be closely controlled. In this case, some run-on plates and run-off plates are being removed after the completion of a submerged arc weld. This process is powered by a Lincoln Electric DC1000 running on 550 volts, which produces 1300 amps of DC output. Back at school, we have various ways we can shape metal, from the lathe and milling machine to the hammer and anvil. Industry has some similarities. ER Curtin have a number of large capacity milling machines which can power cutting heads over 1 metre in diameter. A lathe with a 520mm swing and 1.7 metre centres, and a hydraulic press with 400-tonne twin rams. At school, we have various tools and methods for bending metal, including pipe benders, the pan brake and pyramid rollers. Both of these have a capacity of 1.6mm thick sheet. In industry, there are some similarities and differences. These pyramid rollers at ER Curtin are similar to those found in schools, except that they can roll plate steel sheets 3 metres wide and up to 50mm thick. All of the cylindrical sections found in the factory as part of the current build have been formed on this machine. ER Curtin does not use pan brakes as they are specifically designed for the bending of sheet metals. Pyramid rollers are unsuitable for forming smaller diameter cylindrical sections. In this case, the hydraulic press is used. This is quite a time-consuming process, as the angle formed must be checked and rechecked for accuracy. The required tolerance in this case is 2mm. ER Curtin uses gas metal arc welding and submerged arc welding as their main metal joining processes, in many ways similar to schools, but on a larger scale. The welding machines are connected to a 3-phase 550 volt supply, which is more than standard 3-phase at 415 volts. This allows for higher capacity machines to be used and much longer duty cycles. Here we can see a process known as submerged arc welding in action. In this process, instead of a shielding gas forming an oxidisation barrier, a silica-based product much like a coarse sand is fed from a hopper onto the weld area. The arc and the weld pool are completely covered by this material. An extremely even and high quality weld is produced. In this case, 50mm steel plate has been rolled into cylinders. The join is being welded and filled by up to 7 runs of the welder. The consumable electrode in this case is 4mm thick, the thickest gauge available on this type of machine. Here we can see a completed weld on the inside of the cylinder and a partially completed weld on the outside. The extra piece is called a runoff plate and will be removed at the completion of the weld process. The welding machine is mounted on a welding positioner, which is over 2 stories high and 10 metres long. This allows the welding operation to be either semi or fully automated. The welding operations use a significant amount of consumables, such as shielding gas, welding wire, and submerged arc welding flux. Let's have another look at the submerged arc welding process. Here we are coming to the end of a run on the cylinder. The cylinders are to become pulley wheels for a giant drag line excavator used in the mining industry. Each cylinder weighs over 750 kilos. Some of the flux melts, which forms an almost perfect oxygen barrier over the weld area. The lateral movement is preset into the welding positioner, with the operator only making minor vertical and horizontal adjustments. Note, at the end of the weld, the thickness of the welding wire. At school, we may use a number of techniques to finish metal, such as hand grinding to remove excess weld material or splatter, or brushing with the wire brush. We may paint the material or even electroplate. Industry uses all of these techniques and can also use other processes such as galvanising, sandblasting or anodising. ER Curtain does not extensively finish their products on site apart from grinding excess weld material, but they do have a furnace that they use for stress relieving, which is an important finishing process, as well as a furnace for quenching, normalising and annealing, with 1220mm width and 1524mm depth. That brings us to an end of our look at industrial metalwork processes. From this video, some similarities and some differences should have been apparent. If there was anything you were unsure about, take time to read the information sheets that go with this video. Thank you to the management and staff at ER Curtain Proprietary Limited and Wycliffe Christian School.